eliminated spatial redundancy. So this is one of the example for the run length coding. So we have to identify the correlated adjacent bit values, and we have to identify and it will be represented in a 2-bit representation. For an example, from the given example, the consecutive ones are 5. 1, 2, 3, 4, 5. The consecutive zeros are 5. Consecutive 2s are 2. So it is rearranged as a 1, 5, 0, 1, 2, 3, 4, 5 and 2, 2. So these are the representation of the run length coding. So nothing but here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bit of transmission is represented in the form of 6-bit representation. So this is the example for the run length coding. So this is the identification. So nothing but the condition is to apply the run length coding to high frequency alternating images. If the different pixel values in the matrix or images are irrelevant, there is no correlation between the overall pixel values, means we not able to apply the RLE. If we have to apply the run length coding, is the compression ratio is very minimum. So for that, whenever the data, the information sequence of data or matrix representation of the highly correlated adjacent values, we have to use the run length coding. So first we have to encode this exact sequence using run length coding pairs with values comma count. The corresponding values with the number of repetitive count will be represented as values comma count. After that, to calculate the total numbers of data points in the new encoded sequence, thus the result is compression or data expansions. So these are the things we have to discuss for the run length coding. After that, the bit plan coding. So this is the bit plan coding representation. If the gray level image will be separated with respect to 8-bit representation. If the image have the 8-bit representation, means it will be separated into MSB to LSB. The MSB is represented bit 7 and the LSB is represented bit 0. So if they are separated, nothing but the bit plane is separated into 8 different planes. The corresponding value is separated, nothing but it decomposes in a m-bit image into m separate binary images. Another one is a higher order planes naturally exhibit with a continuous area of zeros and ones. Finally, binary compression like run length coding and complex photographs. So if the data will be in the gray level or a huge color variation, we have to implement it in the bit plan coding. So these are the representations with the standard based to binary values versus grayscale values. Here we represent the 0, 1, 2, 3, 4, 5, 6, 7, 8-bit values. It will be flipped, means the value is we given to the invert. We find the 0 is converted into 1, the 1 is converted into 0. So this is the 8-bit flipped data. So the same thing will be applied for the gray solutions, means the successive code will be differ by only 1-bit position, preserving continuous run of zeros and ones for RLE. Here we have to, whenever the value is, the first value will be flipped, the bit 1 value is flipped and the other value is already we have to transmitted or we have to position as a same. So this is the two representation. Here the standard base 2 method, here we flipped all the 8-bit representation. Here we have to flip the MSB bit only. So in LZW, the input of stream of data is given to the sequence matcher, and finally we updated with the dictionary update, finally converted into fixed length output index. So here we assign the fixed length of code word to variable length sequence. Scan the data for longest existing sequence W plus next character K. This is example. The output of index value for W, progressively adding WK to the dynamic dictionary. So nothing but other than that, the data will be a new character. We have to update the dictionary to provide the value. So nothing but it requires no prior knowledge of symbol probability. So in Huffman coding, we have to identify the symbol probability with respect to 0 to 1, and also we have to combine the least LSB bit with combined together to produce a new value. After that value is combined with the next higher order probability value to generate the code. But here we have to continue without knowing the prior information about the signal. We update the dictionary whenever the new code will be given to the LZW, produce and update the new dictionary word. So next there are the different methods, nothing but this is the summary of the Huffman coding, run length coding, LZW coding. So these are all the concepts come under the lossless compression technique. So nothing but it serves as a crucial back-end compression component in JPEG images, MP3 audio and text file zipping. So these are the techniques come under the Huffman coding. For run length coding, we have go for the facts and simple BMP image encoding. So these type of extensions we go for the run length coding. For example, facts or any other things, the encoding run length encoding technique will be applied. Finally, for the LZW coding, the algorithm which stands behind the GIF format, TIFF images and PDF document compressions. So these are all the applications whichever the data will be used for the coding technique for compression. So for JPEG and MP3 audio and text file zipping, we using the Huffman coding. For Facsimile and BMP bitmap images, we using the run length encoding technique. For zip format, TIFF images and PDF, we use LZW coding. So these are the lossless compression technique for the different applications. So these are some differential applications for the run lossless compression technique with Huffman, RLE, Bitplan and LZW. So this is the target redundancy. So the different redundancy techniques are available. For Huffman we go for the coding. For RLE we go for the spatial. For Bitplan we go for the pre-processing in a spatial. LZW we go for the spatial. For the key features with respect to required probability data, in RLE ideal for binary runs, requires gray code, dynamic dictionary. So these are the key parameters used for to compress the data in Huffman, RLE, Bitplan and LZW. So the type of output is in Huffman it is a variable length binary. For RLE value count pair representation. For Bitplan binary matrix representation. Finally for LZW fixed length index will be the output of the lossless compression techniques. So these are the representations of lossless compressions. Why must medical diagnostic image rely strictly on lossless architectures rather than high ratio lossy methods? If an image has an equal probability of all pixel intensities, will Huffman coding provide significant compression? Why or not? And the third one is here. This is the review questions that explain the mathematical reason stands behind decomposition is detrimental when preparing an image for run length coding. So here the lossless compression is guaranteed the perfect data reconstruction. So lossless is nothing but the x of n is a input data, x cap of n is a output decompressed data, x cap of n is equal to perfectly equal to x of n. This is the lossless compression technique. After that, the efficient system designs to retrieve the matching the algorithm to the specific redundancy. So based on the our input, we have to choose the redundancy technique. For coding redundancy is minimized via the variable length probability, nothing but Huffman. If the spatial redundancy is minimized via sequential pattern grouping with respect to RLE and LZW. So the data pre-processing such as gray code decomposition often refers to unlikely maximum algorithm performance.